Okay, I've got quite a lot of content to get through, I'm afraid, so it's probably...
Time's on our side.
Okay, well, that's a good thing then. Yeah, so we're talking about global heating, and I suppose it doesn't really massively fit into the rest of the theme for the conference because I'm going to talk about the asset that we've already got, but we mustn't forget about that, obviously, and we've got to make sure that we're looking after it and maintaining it and getting the absolute best value out of that. Oh, there we go. So, what am I going to talk about today? So, we're going to talk about what the problem is, touched on it a little bit. We're going to talk about a research project that we've been undertaking for National Highways, for E, and Puru Loganathan, to look at how we can address the effect of global heating on concrete pavements. I'll tell you a bit about the team, some definitions, because there's some interesting stuff in there. It's not perhaps as simple as we thought right at the start. Talk about compression failures that have occurred on the strategic network already, how we've analysed our data, and then look at some preliminary outcomes and some conclusions. We're partway through the project. The project isn't due to complete until early next year. Oh, there we go. So, what's the problem? Concrete pavements, as I'm sure you all know, represent about 4% of the strategic road network. Compression failures are a particular type of defect unique to concrete pavements, sometimes referred to as blow-ups. I'm going to try and stick to the phrase compression failures because it does cause some confusion with pop-outs, as David pointed out, but I am going to try and call them compression failures in this presentation. They occur suddenly and without warning, and obviously that's a massive issue on the strategic road network carrying lots of traffic. And it can lead to severe congestion because we haven't planned it, and massive disruption to the stakeholders. Importantly, with the effects of global heating, rising temperatures, extreme weather events, the chances are these types of defects are going to occur more frequently in the future. So this is about planning to deal with that. So what was the project scope? We're looking at approaches and methodologies to develop an assessment method for identifying and managing the risk of concrete blowouts. There you go, there's another slightly different term. That's why we're going to try and stick to compression failures. So what were our objectives? So we need to develop this assessment method to determine which locations on the SRN are most at risk from these types of failures. And then we need to suggest some remedial actions. How are we going to fix them? That could be things like full depth repairs, bay replacements, etc. And then we need an asset management strategy to make sure that those people who are managing the strategic road network on behalf of National Highways know what to do to try and predict when these might happen and what to do to remediate them when they do happen. Just for interest, there's a photo there of the A14 in Suffolk, and you can see that deterioration in the concrete pavement there. Who was the research team? As I said, this research was for National Highways. E is our project sponsor along with Puru. Then we've got a team within Atkins Realis who are delivering the research. We've obviously got our stakeholders within National Highways, including the Concrete Road Centre of Excellence, but also Operations Directorate, because they're on the sort of sharp end, if you like, of this. They're the guys that have to deal with it when it happens. We've also been liaising with a specialist in South Korea, Professor Seong-Lee Woo, and he's done quite a lot of research recently, particularly about trying to predict when these compression failures might occur. So that was not officially part of the project, but it was a nice sort of link up to see the work that they're doing in South Korea. Okay, definitions then. Here we go. So, a compression failure, the localised upward movement or shattering of a slab at a transverse joint or crack. It occurs when the volumetric expansion in the concrete pavement causes a transverse joint or crack to close up, such that no further movement can be accommodated, historically also referred to as a blow-up or possibly a blowout. You can see from the diagram there, it's not exclusively to jointed concrete pavements. It can occur in a continuously reinforced concrete pavement. And in fact, we've got examples on the strategic road network where that has happened. So we definitely know it is true. But typically people tend to relate it to jointed pavements, either reinforced or unreinforced. So essentially what you're having is two slabs coming together with a joint in between. That may be a contraction joint or an expansion joint. Two slabs come together, they can't move any further, the concrete is expanded under the heat, and bang, up it comes. Can also happen where a concrete pavement is terminating, particularly against a bridge abutment. That's probably a slightly more unusual situation for the UK because we would normally have a transition before we went to a bridge, but in the States that's a more common way that it looks. And if I just nip back, if I can, there we go. So what you can see there, what you can see there is exactly what's happened. Okay, two concrete slabs, they've come together, they've pushed up, and the concrete has effectively exploded at that joint. Obviously, that's a massive issue for the travelling public. It's very dangerous. If a car was to drive over that, or a motorcyclist was to ride over that, it could be really, really serious. So it's very important that we know when these are going to occur. I'm going to go on about definitions quite a lot, sorry, but sometimes people refer to these as heaves. And this can be confusing, and we would recommend moving away from that terminology because heave has got a specific definition in the Concrete Pavement Maintenance Manual that's to do with uplift of unbound subbase and subgrade. Okay, but in this particular example, you can see in the photo here, because there's asphalt surfacing over the concrete, it was described as a heave, and it is. It's a joint up. But until we know why that's occurred, is that to do with the compression failure in the concrete underneath, we would recommend that those are referred to as a transverse ridge, just to move away from that confusion. And then obviously once we know, is it in fact a compression failure in the concrete underneath, or is it something to do with the foundation, we can choose which terminology to use. So it's all about generating pressure in the slabs. And what you can see here is a bit of a time step through what might happen when a compression failure occurs. So in our working pavement, we've got some nice expansion joints in our concrete pavement that allow it to expand and contract. If those joints are closed up for any reason, through purely expansion, or perhaps because there's something in the joint which stops it from functioning properly, essentially what happens is all those joints are then closed, the pavement doesn't have anywhere to go when the temperature increases again, and you get that temperature that triggers the point where pavement growth can't occur anymore, and your compression failure occurs. So what was the project all about? We had a desktop review where we were looking at what was out there on compression failures, what were other countries doing to deal with compression failures? Did they have mitigation methods? Did they have prediction models? We also looked at the possibility of using condition data to help predict when a compression failure might occur. And then we undertook a feasibility review of how we might rate the risk in pavements of this occurring. Obviously, the key thing for national highways is, can they prevent it from happening? If it does happen, what do they need to do about it, and where was it most likely to be? And then after it's happened, what do they need to do to remediate it, to reduce that risk? So at the beginning of the project, we had some examples that we were given where data was already available for compression failures on the strategic road network. And as just a few, I'm not going to bother to go through the details there, but you can see, importantly, they're on all sorts of different concrete pavements. So they're on concrete with a thin overlay, they're on CRCP, and they're also even on rigid composite pavements where you've got a thick asphalt overlay, and obviously on uncovered concrete. So it's happening all over, and it's not restricted to a particular type of concrete pavement. Summer 2022, at the time, was the hottest summer on record. And there were a large number of defects that were reported across the National Highways network that were described as heaves. Okay, and you can see them on the map there. So more than 10 occurrences, and this is global heating in action. And it included, as I say, lots of different types of concrete pavement, legacy concrete pavement, and evolved. So that's effectively uncovered and thinly covered, and also thickly covered concrete. Okay. And you can see from the map that they're quite widely distributed as well, so they're not all in one region. So the effects of climate was being felt, all the way across England. So we had to develop an evaluation method, and we had to think about what the factors were that would be likely to affect this. And obviously pavement type. We know it happens on all of them, but is it more likely on some than others? Things like foundation type. Is it different if it's got an unbound foundation or a bound foundation? We suspect it's probably got something to do with the time of year that the pavement was constructed, because we know that there's a difference in terms of the state of the concrete, whether it's constructed under cold conditions or hot conditions, and then whether the expansion joints will be able to function if it's been built under cold conditions. Climate, is it as simple as maximum temperature, or is it about how long it's above perhaps a threshold temperature? The concrete itself, lots of variables there: compressive strength, flexural strength. Coefficient of thermal expansion of the aggregate is obviously going to affect how much it can move or contract. Joint spacing, linked to coefficient of thermal expansion. Joint width. Interesting that we found that other countries use significantly larger expansion joints than we do in the UK, but they have associated issues with load transfer problems, so it's a bit of a trade-off. And then the condition of the pavement in general. Does it have a history of compression failures? Is it already towards the end of its life? So loads and loads of factors that needed to be taken into consideration. And then we looked at what data we'd got. Okay, so we need to think about the location of compression failures that we already know about, but then we need to get down to the sort of nitty-gritty. What's it constructed from? What's its condition? Are there any other defects that are stored in another system? And as you can see from the top part of that table, the data probably wasn't in the place that we'd like it to be to make this model, to develop this model. Always we're going to have gaps and we're going to have issues, and we had lots of different data streams that we needed to bring together to really characterize the information we would need to try and develop this model. And then on top of that, we had environment data. So not only current temperature conditions, so the temperatures that the compression of failures occurred that we know about, but what's going to happen under global heating? What's the temperature going to be like in 5 years' time, 10 years' time, and is that going to increase the risk? And one of the big things that we really didn't know about, that all the research said was going to be really important, was incompressibles, material getting into the joints of the concrete pavement that stopped the joint from working as it should do. We all know how important it is to keep joint sealant in a good condition for a jointed concrete pavement to function. If that sealant's not there, small pieces of aggregate, even nuts and bolts, can get into joints, and then once they're locked up, they can't make that movement. And all the international research said how important this was, but it's just not data that we've got or could even get, really. So for the sites that we looked at for national highways, there were 16 sites that they originally provided us with, and when we started to dig in, really there were 7 sites that we could find that we were really confident about. We knew everything about them, got all the data that we could, and we were feeling good. There were another 8 or 9 sites which basically had critical information missing. So we were really restricted to a very, very small data set. So what we did was we had to go away and collect all the information for those and really try and understand what it was that was causing those compression failures. When you're working with a data set that's really only got 7 points in it, even though you've got lots of associated data for each of those 7 points, it's quite hard to do a sort of standard analysis technique. You know, normally we'd have looked maybe at a multiple regression. That's used in lots of pavement design stuff, but unfortunately our data set was so tiny, that was not something that we could do. So we had to look at it in a different way, and we used something called anomaly analysis. I'm glad that's out of the way. Which is a statistical technique that's used commonly in things like the aircraft industry when they want to understand about jet engines and why they fail. They've got loads of data of jet engines at work, and a very small amount of data of jet engines that don't. So in a way, we had the same thing. We've got loads of data about concrete pavements that don't have compression failures, and we had a really, really little bit of data about where they do. So we fed all of that information about the good sites into the model, and we trained it to try and find what was the combination of parameters that would make it say that one's more likely to have a compression failure. And what you can see here in the bottom graph is these ones down here We trained it. We basically gave it some data that we knew was right, and then we fed it some data that we knew where compression failures had occurred, and we asked it to find it. And that's what those 4 points are down there. Okay, and that gives us a threshold. It's sort of like a multi-dimensional threshold for us to find these sites. Okay. So once we'd trained the model and set it going, we asked it to find the top 10 sections with the highest risk of compression failure on the strategic road network. And this is at section level. So this is the pavement management system section level. So it's very granular. These are like typically 100-meter sections. But we asked it to go and find it. And you can see from that list there, very, very comfortingly, the sites that it picked are actually mostly sites that have already been reconstructed. So the highest risk ones had already been identified elsewhere within the concrete roads programme to say these pavements need reconstructing. They're at the end of their life. So we got great confidence out of that. And in fact, A5 Stony Stratford is in the Life Cycle Extension Works programme. So this gave us confidence that the model was really doing what we wanted it to do. So we took those sites out that had been reconstructed, and we reran the model to find our next, top risk of compression failures. Again, this is really great. It's picked out some stuff for LEW, and it's picked out 3 sites, the 3 ones in white there, which now, from a risk of a compression failure alone, in the next 5 years, so in the next road investment strategy period, those sites, the M11, Junction 9A to 11, and the Nursling Spur, are at the highest risk of compression failures on the strategic road network. Now, we're not saying it's going to happen in the next 5 years, and we're not saying go and maintain those now. What we're saying is a strategy needs to be developed to monitor these so that we're ready to deal with it should it occur. And obviously, there's a huge amount of uncertainty built into it because we're using a climate model to model what the temperature will be in the next 5 years. And from looking at those models, we can tell that this is an unrestrained scenario. So this is no change to emissions at all. And what this would show is that in the next 2 years, we're going to get very, very hot summers. And that really is going to increase that risk massively. And then the temperature tails off. Now, whether that really happens, do we get our emissions under control? Do we start to make some dents into arresting global heating? Then that risk recedes. But those sections will always be more at risk than other sections of the strategic road network. Next bit of the project is to develop a data visualization, and this is underway at the moment. So effectively, we're going to use a dashboard type tool, which will allow national highways to drill down into this data and understand what it means. They'll be able to look at it by different pavement construction types for their own region. And the idea of this is to allow Operations Directorate to really get a handle on what they've got in their region. But it also makes it really easy to see what's going on. Sorry, big conclusion slide. I'm not going to read it, but I'm going to tell you what the conclusions are. The conclusions are that we've found a way of helping national highways identify where their highest risk sites are. And the important thing is that can feed into their prioritisation process for future works on concrete roads. It also means that we can use life cycle extension works projects. If those are coming up on sites that are identified for high risk of compression failure, then what that will mean is perhaps the treatments can be targeted to address that. For example, by introducing some new expansion joints. If we're doing a concrete bay replacement, we're doing that by right anyway, but making sure those go in and making sure those functioning and replacing joint sealant whenever we get the opportunity to ward against that, basically. And we've looked at mitigation measures, as I say, internationally, and really the introduction of expansion joints is the number one method of mitigating against this happening. So, that's what we'll be focusing on when we write up the asset management guidance, which is the next phase of the project. Next steps. that asset management guidance, which will look at the mitigating the risks, and that involves all options on the table. Eliminate, obviously that would involve reconstructing the pavement, then it's not going to be there. Reducing it would be adding in your extra expansion joints. There are other ways you could look at it. You could isolate it, so making sure that those high-risk routes, is there a diversion route? Because, again, that mitigates the risk. It's understanding how you can manage it. It's not just about trying to take it away. And control. So if we've got a route that we know is at high risk, do we increase our inspection frequency on that route to make sure that we catch it before an incident occurs, or if an incident has occurred, we catch it quickly before there's obviously damage to the travelling public. Thank you.
Thank you, Donna. Any questions, please? Over to you, Adrian.
Time of year. I have a view that time of year has a massive influence on compression failures. So much so that it's actually best not to construct in cold winter times. Well, is that built into your consideration as risk of failure, pavements that have been built in the winter as opposed to in the summertime?
Yeah, absolutely. We looked at this early on in the project. The problem is, as always, is getting the data. So a lot of these pavements were obviously constructed 40 years ago. We might have a year of construction. We certainly don't have a season or a month of construction.
Okay. So a question is maybe the advice for new design and repair design might consider more movement joints if constructed in winter. In the winter time than in the summertime.
Yep, absolutely. Totally agree with that. We can't say let's build everything in the summer. That's not realistic. But if you are going to build in the winter, including additional expansion joints is 100% a sensible thing to do.
Hi, Donna.
Hello.
That was really interesting. Thank you. I'm Tina McHugh from Costain. In addition to temperature-related studies on failure in concrete pavements, is there plans to, or have you considered the association of the action of drainage or the performance of drainage in addition to that? Because I think rainfall, additional rainfall, lack of attenuation, maintenance and so on, all play a part in failure of all pavements. Yeah, absolutely. So again, early on in the project, we tried to look at whether there was any impact of the combination of large rainfall events combined then with high temperatures. Some of the literature indicated that might be an issue. We couldn't find anything in our data, but we have included rainfall as part of the overall model. It's one of the parameters in the model. But as you say, any pavement, you're expecting it to perform as you designed it, and that didn't include the foundation being saturated. So anything we can do to keep the drainage in good condition has got to increase the life of the pavement. So agree, yeah.
No further questions? Or one at the back?
Morning, Donna.
Morning.
David York from Blue Phoenix. Just a pretty obvious one you probably have taken into account, but the thermal expansion coefficient of the aggregate?
Yeah, again, yep. So what we've had to do is we've sort of had to take a proxy. Some of that information is available in CPAM, the National Highways Pavement Management System. What we did is we searched for the sites where we knew we had a compression failure, and we went into the detailed records, and we did manage to find some core logs. So we made an assumption of CTE based on the aggregate type from that. What we don't have to then feed into the wider model is that information for everywhere. We looked at whether we could make an assumption based on joint spacing for URC. Obviously, 6 metre bay would mean that it was a limestone aggregate, and 5 would mean it was gravel or other. But again, we couldn't find, there is some in K-Portal, some joint information, but we couldn't find total coverage, but it's still something that we're thinking about whether we could fit that in, because it's got to be a massive issue, and it would help refine the model to find those high risk sites.
Your maps sort of reflected flinty, gravelly areas.
Yeah. We looked at the BGS as well, so you can make some assumptions around it. But in terms of the model, it makes it a little bit tricky to include it in the output. Thank you.
Any further questions? Donna, you're off the hook. Thank you very much.
Thank you.